So my name's Bill O'Farrell. I'm the Senior Technical Manager for Go on zOS. And I'm going to talk to you today about Go on zOS, and I'm going to talk to you about crypto and kind of a mix of both greatness of Go, some of the capabilities of Go, and we'll definitely be talking about crypto as well. So if I figure out how to share screen. Okay, I'm going to share my desktop. And I'm going to start the talk. And now I'm going to show, slideshow, play from start. Okay, I apologize for not having the right. This is Share Orlando, where I last did a talk like this. It's not the right header slide, but nonetheless, all in the family. So what we're going to talk about today, first of all, is we're going to do a brief introduction to Go on zOS. So some of you may or may not be familiar with Go. It's a relatively new language, and I want to make sure that we're all on the same page as to what Go looks like and what it can do. I'm also going to talk about a new capability that was just introduced on zOS on March, I think it was announced on March 8th of this year. Sorry, change slides, which is a native container. So Go is the first programming language available in a native container on zOS. So I'd like to demonstrate that. I'm proud of our ability to interact in a container, and we were the first one. Also, of course, as you could gather from the title of the talk, we're going to talk about crypto libraries in Go and how they're accelerated. So let's kick it off. The official name of the product is IBM Open Enterprise SDK for Go. So what is Go? Sometimes called Golang, by the way. Well, it's a relatively new language, 12 years old, with a simple syntax. It's lightweight, easy to understand. Very important, it's memory safe. So in today's world, we've been directed at the highest authority to use memory safe languages. That means languages where you can't make mistakes with memory allocation, which give you often intractable bugs due to mistakes in allocation, deallocation, et cetera. So it's memory safe. You can never get tripped up in Go as far as the use of memory. It's a perfect fit for microservice architecture, fast running due to small syntax, concurrency support, and highly scalable. And it's very clearly want to make sure that you understand it's a compiled language. It compiles to native machine code. It's not emulated or simulated. So unlike, for example, Pascal, which is simulated at a bytecode level, it doesn't have a JIT. It's a real first-class compiler. It has a powerful standard library of packages and built-in features to support application development, very strong backwards compatibility guarantees. This is one of the reasons why it's so perfect for zOS. So Go guarantees that a program you write now will continue to run and to build and run essentially forever. Go groups programs into things called modules. I'm going to show you a little bit about that. And in the module, you're going to tell Go what version of the language that you expect to compile it with. And it's going to respect the rules of that version forever, essentially. So even if the language makes subtle changes, usually to fix bugs in the future, when you, let's say in the future, 10 years from now, you get the latest Go, and then you build your program, it's going to respect what you said in the module declaration, and is going to build it as if it were that version. The important thing is that it will have all the latest vulnerability fixes. So you always have the best, most secure Go program when you build with the latest Go. Go is an open source project and with active and vibrant community and cross-platform support. It's really emerged as the language of the cloud. All of the cloud software, virtually all cloud software is written in Go these days, including Kubernetes, Podman, and Docker, and uh, all of these um, products and rapidly increasing number are written in Go. This is a no-charge product, and we like to emphasize our versioning. So we have essentially we're still on Go 1. We're up to Go 1.22, and in August sometime we'll be on Go 1.23, and on it goes. It will never flip over to 2. So that's a statement of the backwards compatibility for Go, is that it will never flip over to an incompatible version. It's the fastest growing in the open source community. On the GitHub pull requests, it's 5th in number in terms of languages. And there are 9 million unique installations of Visual Studio Code for Go. All right, if I can get this
Hey,
to
Bill,
flip.
I have a quick question from the chat. Stuart asked, from a mainframe source code management point of view, does it persist in PDS members, like fixed block, with a restriction on the line length, or is it Unix system services?
It's Unix system services.
Thanks, Bill.
Okay, thank you. I just wanted to give you a little taste for the syntax of Go. I just threw this in at the last minute because I just felt that you should see a little bit of Go. So this is a program. It's a piece of a program. It's not the whole program, but it's a piece of a program which reads data and collects it. It's from, you can look it up, you can Google it. It's called the billion line challenge. You're supposed to read 1 billion lines of text and figure out how to do it fast. So just to give you, this is just a snippet, but some of the unique things in Go, you can see you have multiple return arguments. So OS open will return a file descriptor and potentially an error code. And this underbar says, it's nice that you return error code, but I don't want to look at it right now. So I put an underbar, which means I'm not actually going to check it. And colon equals, this is a unique Go feature. This is implicit declaration. So although it's a type safe language and everything is checked in terms of type safety, it looks like it has dynamic declaration, but it doesn't. This is just a syntactic sugar, whereby you don't have to explicitly declare a scanner. It gets declared implicitly by the use of the colon equals. Now it's got for loops, which of course are standard in C, and it may look a lot like C to you. But it also has, for example, a very strong library. So here, for example, in the library, we have something called buffered.io as a package that we're using, and it has scanners that we can use, and it can scan for text. So all of that stuff is built in. So all of this does in the sequential solution is to read a line of text and then essentially parse it. Okay, so we're parsing it here. We're looking for, I think it's I can't remember the syntax for the billion line challenge, but it has a certain syntax of text, and we have to parse it to find that text, and then we basically catalog it by doing this merge operation. So that's what Go looks like. And just for fun, I thought I'd throw in how Go differs from many other languages in that it has built-in concurrency. So just very briefly, it looks much the same, except now I'm going to make something called a channel. I make a couple of channels. Channels are how you can do communication across concurrent processes. And it has the famous Go space and a function name. Instead of just calling worker, I could call worker in a Go routine, which is like a lightweight thread. And now I'm spinning this off concurrently. The wait group allows me to count how many of these I've spun off. And at the end, I can just wait until I've had that many returns, and then I can aggregate them together. So that's a very, very simple syntax for introducing concurrency into your program. And the results with that very simple concurrency application are that it runs 3 times faster than it did before. So that, and there's a lot more that we could do for performance, but that just illustrates concurrency as one of the primary features of the language. So now I want to, as further aspects of what Go can do for you, I want to introduce the Go within the zOS container platform. So we've been available as an on-prem programming language now for several years. I've kind of lost track how many years. I think at least 4 years, maybe pushing 5 years. We've been available as an on-prem language that you could download. You can get support for it, so you can acquire it through ShopZ and pay for support. Or if you just want the open source version without support, we make it available as a PAX file. You can just unpacks it and you can use it locally. Either way, that makes sense for you. But since March of this year, we've also been available in the IBM zOS container platform. So you may or may not be familiar with containers. Containers are kind of like lightweight virtual machines, except very heavy emphasis on the lightweight. Um, they are a key part of application modernization and co-location because they allow standard DevOps pipelines now to be built on zOS with zOS native technologies, whereby you can co-locate your deployed containerized application on the same machine where your data is. And of course, it's based on industry standard open source technology. So we're using Podman, we're using Kubernetes, not quite released yet, but it will be soon. We're using all the standard container technologies that if you hire a new person, a new graduate, they will expect you to have this stuff because they're very, very familiar with it, because it's been around at least for a decade on Linux platforms and now available for native zOS application development. So that improves the developer experience and allows you to orchestrate your containers in well-known ways to respond to changing loads, changing requirements, etc. So that is the zOS container platform. Now, I
Hey, Bill,
think, yes.
can I turn to quick? Yeah, we have some good questions from Stuart. I'll probably unmute Stuart at the end. Stuart asked about what does concurrency look like on zOS execution? Is that something you want to just shoot from the hip, or we could save that for later?
So, sorry, I'm going the wrong way. Here we go. Yeah, so this syntax here is a way of spinning off a Go routine, which is like a thread, except as a very lightweight thread. So when you deploy your application, you're going to either choose the default or you can specify the number of actual pthreads that are created in order to run your application. And pthreads are scheduled on real processors. But the Go routine is a lightweight thread, so we can have potentially several, and sometimes several hundred, and sometimes even several thousand Go routines scheduled on a single thread. And they are scheduled by the Go runtime rather than by the system runtime. And so the reason that we're able to, for example, get this speed up here is that, and you could potentially even see speed up even if you ran it on a single core, is because the Go routines are scheduling, and so that you're not stuck waiting for the next input. You can process input as it comes. I'm not sure if I'm answering the question, but that's the general principle for concurrency in
Awesome,
Go.
thanks, Bill. Yeah, probably what I'll do, I'll let you carry on, and then I'll unmute some of the folks wanting to ask questions, and we can kick off a dialogue at the end. I know you've got lots of great slides. Thanks,
Okay.
Bill.
Yeah. So I think what I'm going to do here is a demo. So if let's see, does this work? Yes, that worked. Can you see my demo screens here?
Yeah, we can see a couple of shells. Your front one, your ZS8 shell, yeah, they all look. Your ZS8, one of them looks a little bit small, but what we can see right now is
Okay,
your.
I'll expand
Um,
that one momentarily. Okay,
that's great.
so
Thanks.
we'll first focus on this one. So this is a little Proverbs is a little module that I built just for demonstration purposes. Okay, so it's a Go program, and I've built it already, so I can run it, and it prints out pithy proverbs, including "Ahoy world" and "Concurrency is not parallelism." Um, there's a this is available as an open source project in order to demonstrate Go and modules, etc. So I pulled it off the web, but I just wanted to show you what are the parts of a Go module. So the first part of a Go module is go.mod file. And this is when I said that you can specify the exact version of Go that you use to build your module. Here it is in the go.mod file. First of all, I give it a name, and I tell it this is built with Go 1.22. And then we list modules that we're dependent on. So the primary dependency here is a module called rse.io. This is a website with a repository. Quote is the name of the module, and version 3. So Go supports versioning of modules. In addition, I have the indirect dependencies listed. So this module is dependent on a bunch of other modules, 2 in this case, and so we're going to list those there. You don't have to do that manually. That Go picks that up for you and lists them and puts them in there automatically. In order to make sure that when we do build that we're getting the exact dependencies that we specify, we also have a go.sum file. Again, Go builds this for you. You don't have to do anything. And it's going to have these cryptographically secure hash codes in order to identify the actual code that you're downloading to build your module to make sure you are guaranteed to get the right code. No one can slip in, malicious code, because that would change the hash code, and you've got that secured in your go.sum file. So those are the two sort of, I'd say, bookkeeping aspects of a Go module. Then, of course, we have the Go code as well. And yeah, so this is a full-fledged Go program. This is the main package of the program. Some imports. This FMT is part of the standard library. There's like a whole, I don't know, dozens of packages that you can import that are available directly with Go from the standard library. And this is the one that we got from external repository, quote v3. And it just has 2 print statements where we're printing a couple of proverbs. So it's a very simple program. So one thing I wanted to show you in this window, if it works, Go comes with a vulnerability checker. It's something you can download from the web. Developed by Google. Go originally was developed by Google. And this is maintained up to date, day by day, all of the registered and known vulnerabilities that may exist in various packages that you may be using. And so as part of your build pipeline, you can put in a vulnerability checker to ensure that you haven't accidentally stumbled into a vulnerability which has emerged and been registered in the vulnerability database. So all I've got to do is go vuln check dot slide. This is a bit of Go syntax saying all this module and all submodules. And it's going to, I can quickly, I ran it just before the demo here. It's going to quickly say that in those modules that I imported, there were 51 packages across 4 dependent modules for known vulnerabilities. There were no vulnerabilities found. However, the scan did find 2 vulnerabilities in packages that I imported. And in one vulnerability in modules I require, but I don't actually hit them. My code doesn't appear to call these vulnerabilities. So So nonetheless, I can carry on with this module because it has no actual vulnerabilities, just suspect code and stuff that I didn't use. So it's very thorough in that way. So I would recommend putting Go Vuln Check as part of your standard build pipeline. Um, so moving on a little bit, um, I promised you I'd demonstrate this in a container. Now I'm hoping this demo works. Um, Demos are always subject to Murphy's Law here, but if I cd containers go, I am running in a provisioned machine that has the Go container runtime installed. And what have I got here? I've got something called a container file. So everything that runs in a container typically has a container file associated with it. So I'm going to look at my container file, and this container file tells the container runtime how to put together a container instance with the application that you want to run. And these are the syntaxes you see inside of a container file. So I'm going to take the latest zOS, first of all, and I'm going to take the latest Go. Now, remember I said that the very best Go to build your application with is the latest Go, because it's guaranteed to be backwards compatible with your application, regardless of when you wrote it. And the latest Go will have all the latest vulnerability fixes so that you'll have the most secure program. Then a few setup things. So I have to set up a working directory. This little piece of boilerplate ensures that I set up my environment for Go, because Go needs a certain set of environment variables set. Then, as is done with Docker, so our predecessor in the Linux world was Docker, you typically would copy the Go mod and Go sum files. Go mod download means you're going to actually download all the dependencies that you need to build your application. You're going to copy in the Go files, and then you're going to build them. So that's how you construct a container file to build the Proverbs application. And the command here says, when I run the container, this is the command that's going to run. So I can do that. I've just done this recently, so hopefully it still works. I'm getting it from my history. Somewhere in the history here. Nope, sorry, there we go. Okay, so I'm going to build my application. This is the build step. And so I'm invoking Podman here to build the application. It's pulling in zOS latest. It's pulling in the Go compiler at this point. And everything else, because I did it before, everything else is coming from cache. So every line in the container file essentially gives the system an opportunity to cache the result. And this is really what makes container files very efficient, or containers in general, because instead of having to replicate everything into a virtual machine, everything is stored in the container cache, essentially. And now I can run that application. What I'm going to do when I run it is I'm going to deploy the instance of the container. Sorry, I've got this deeply in history here. Looking for the run command. There it is. So I am instantiating the instance of the container, and I'm running it. And there it ran the command, hello world is printed and concurrency is not parallelism. So I printed my pithy proverbs, and that was part of a container instance. And I can deploy that container instance on other machines that are running the container runtime. I can, for example, play with the IP addresses. I can have multiple container instances on this one machine, etc. So that's all part of the deployment flexibility that containers bring you. One more thing I wanted to show you is the multi-stage build, because I think it's really cool. So if I want my containers to be very thin when they're deployed, I can go through all of the steps that I just went through in order to build my application. And then at the end, I can introduce this from. Remember, I had a from up here. I added a name here as extract. I introduce a new from, and that essentially says all of that stuff, those build tools, etc., that you were using to build your application, we don't need those in the running container. So let's start from scratch here and get the latest zOS, and let's get the application from that previous container instance noted above. And now when I deploy this container, all I've got in it is the application. I don't have any of the build tools for a slim deployment. So that is a standard technique called multi-stage build. I just want to show you how that works. I'm not going to run that right now, lest I invoke Murphy a bit too much. So that is, I'm going to pause for questions right now because I'm going to go on to the whole new topic of crypto at this point.
So Bill, that was phenomenal. I have a couple of questions I just want to shoot over to you, and anybody else wants to use the chat. So were you running on the IBM zOS container platform there? That's what we saw.
Yes.
Cool. So for those of you who didn't know, that's really fresh. That only actually just got announced and released, I think, on the 5th of March. I did a quick Google. So the paint's still quite wet on that. I'm sure within IBM compiler team, you've had it available for a long time, but that's pretty
Yeah,
cool.
we've been playing with it for a while. That's right.
You've been playing with, you've had a bit of, but that's phenomenal. A lot of people have been looking forward to that tech. Also, you're running and you just SSH your way into an LPAR, right? Into USS and an LPAR.
That's right.
Logged on as root, and that's TVT 5002. TVT is what I guess Toronto virtual. So it's some provision system that you have running in the Toronto IBM infrastructure. Yeah.
That is correct.
And you're also, looks like you're using Bash and Vim. They're not natively available under USS. So you must have gotten them from somewhere else.
Okay. So, yes, when we provision this machine and set it up, we put in the standard tools that we're familiar with. So Bash and Vim are there, yes. Actually, Bash and Vim are available on another of our projects called the Z Open Tools project. So if you want the latest tools, Bash, Vim, Git, Perl, less, trying to remember the big list. Anyway, there's actually about 200 tools that are available on Z Open Tools. That's open source. You can download them in binary form, and they're maintained continually. So we got our Bash and our Vim from Z Open Tools.
Yeah, I did actually. Yeah, I did bait you with the answer. I sort of knew that was the answer. I posted it in the chat, if folks. I didn't want to turn this into a zOS Open Tools discussion, but yeah, there's an awful lot of ports. Yeah, Bash and Vim are the great ones. Curl is another cracking thing. So if you're doing anything productive in Unix system services, there's an awful lot of goodies in that goodie bag, definitely, for sure. So one other question before you get onto crypto. So a lot of the reason that a lot of non-mainframe languages are ported to the mainframe is because a lot of customers are trying to access other services that the mainframe has. So for example, let's assume that within Go, you wanted to submit a job or issue a TSO command, or perhaps interact with the MVS file system, perhaps read data from a vsam file or something like that. I know Java has a JSOS library. I know Python has a PYRACF. There's a bunch of libraries on NPM that basically give you that sort of native binding that let you break outside what would be available in a cross-platform Go or Java program to one that was more embedded. And perhaps you might be writing some modern Go that actually perhaps wants to make a call to something else that's running just side by side. Like maybe make an exec kick. Is there anything like that in the kit bag as well, or not?
Yeah, so we developed a library to access data sets, including vsam data sets. It's called Go Record IO, so you can just Google that. It's on the IBM Runtimes open source site. So that allows you to do everything, including highly performant record IO from a vsam data set. And we have within that Go Record IO, we're continually adding facilities to access MVS services. We have an example of how to access RACF services from Go directly. And so we can access and use, for example, 31-bit services as well as 64-bit services. It happens to be the case that Go, I didn't mention this, Go has its own assembly language. It's built in, it's available to every running Go application. It's not HLASM, it's its own assembly language, but it's S390X assembly. But it makes it very, very easy for us to very quickly drop into assembly without any linkage conventions, etc. We just drop into assembly. We could do some 31-bit work and drop and pop out again, and so on and so forth. So we have a lot of that stuff demonstrated in our Go Record IO library. And we're constantly adding, more of those facilities, but definitely MVS callable services, RACF, and data sets. We have those available now for use. Data sets are particularly easy to use because we've basically taken the data set APIs and hoisted them to a Go level syntax to make it essentially very, very easy for a Go programmer to use those things.
And that's nice. And then that's all going to be running under the same ACE. So it's under the same authenticated shell. You don't have to make another. So it's all just going to be running under the privileges and permissions that user has. So if they start doing things that they're not allowed to or whatever, SAF's going to basically bark at them, presumably.
That's exactly correct. And it barks at us all the time. Then we realize, oh, I don't have that permission. So.
Excellent. So one other thing, maybe you can save this one for the end. So there's a lot of languages coming onto the platform. I know, and they're all trying to find their sort of sweet spot. Java is the kind of line of business sweet spot to be the kind of, it plays in the same, game as, COBOL, for example. I see Python is playing in the same pool as JCL, for sort of scripting and automation for bringing up other workloads. I was just curious where you see, what people like to do with Go and where that's going to fit into a mainframe ecosystem.
Well, a couple things. So first of all of this container product that we've just announced, released, is all written in Go. So that's one of our primary application areas is system software. Okay. And of course, we are a very popular language. So it's also a skills play that if people coming into your organization will much more likely have already Go skills or be readily able to pick them up. And we're experimenting with interoperability. So one of the areas we're experimenting with is interoperability with HLASM and with other languages. So I don't know if we have the killer app yet. But that is an area where I'd say that Go is procedural. It's not an object-based language, and it nicely fits with a procedural orientation. For example, the assembly HLASM has a very procedural orientation. So we're exploring ways that we can interact with assembly. And you'll have to stay tuned for that because I don't have much announcement today, but that's an area, a direction for us.
That sounds really exciting. So it's like, because I know C is available at LEC and Metal C on zOS, but they haven't really gained traction apart from a few niche things and tools vendors. But being able to have a high level language that can basically be as powerful as assembler in terms of the execution set, that's really interesting. So thanks for that answer. Anyway, I'll be quiet and let you carry on because you're about to talk about crypto. Thanks,
No
Bill.
problem. Thank you. Okay, so we're going to talk about crypto. Yeah, so Go has an extensive set of crypto libraries. And we directly implement standards such as TLS 1.3. We don't use OpenSSL. It's all native Go that we have. This offers the opportunity for acceleration with Z hardware. And we have accelerated the following so far: SHA-1, SHA-2, SHA-3, Poly 13.5, SHA-20, AES stream ciphers, CBC, CTR, and GCM, elliptic curve, ECDSA, and ECDH, and MD5. The reason or the result is that under the covers, crypto runs fast so that your applications can run fast. I know that we had one experience where a partner, you can look up the blog, but he wrote a blog about use of MD5 and Go and found it to be 6 times faster than a certain other programming language, which I don't want to besmirch by mentioning it, but you can read the blog and find out which one it was running on zOS. And that's because of the work we've done in the background to accelerate all these things. Now, I have this diagram. It's actually a Z15. I haven't gotten or managed to find the Z16 diagram, but there's a little block down at the bottom here called coprocessor, and that's where the CPACF instructions are residing. So CPACF is, I forgot the acronym already. I thought I'd remember it. Facility for Cryptography. Anyway, it's how we accelerate a number of the algorithms that are available in Go. And ones that don't reside in CPACF, we've actually manually coded them in assembly, Go assembly, of course. So as an example, we have accelerated ECDSA, that's elliptic curve digital signature authentication. And that can be done with a single CPACF instruction. SHA-2, SHA-3, again, a single CPACF instruction. Not so lucky on SHA-20 Poly 1305. This is probably the most popular stream cipher that's currently being used in the wild, and it's not yet on CPACF. But we actually put in a lot of assembly code to accelerate it, and I'll talk a bit how we did that. So I just wanted to point out, these instructions, when I say KDSA is a single instruction, it has 15 pages of description on how to use it. So it took us a while to figure it out, but nonetheless, it's a very complex instruction, but it does run very fast. And in order to prove, our results here, you can actually benchmark this stuff yourself. So for example, if you just go into a directory, and by the way, Go is always distributed with entirely with source as well. So it's an open source language, and we always distribute all the source with Go. So you can CD to any source directory, and you can go type this little command here, go test dash bench equals bench. I know that seems silly, but this is a pattern matching thing, and dash, when you do capital BENCH, that means you get all the benchmarks. And so, for example, here are 2 benchmarks results that we got running on, I think this is a Z16 that I ran these on. So I want to compare these to a machine that I happen to be running on, which is my Mac. This does not besmirch the Mac in any way. I really like the Mac. And this is, it's not the new Mac, it's the old Intel Mac. But I've got Go here, and I'm going to, I've CD'd into the, let's see, source crypto ECDSA directory on my Mac. And I'm going to run that benchmark. So go test dash bench equals bench, and it will run through the ECDSA benchmarks, and then we can do side-by-side comparison if we want to. I'll just pick out the first 2 here because I've got to change screen in order to, let's see if I can, maybe I can iconify this. That makes it easier. Maybe I could just move this over. That's how I do it. Okay. So it's going to give me a result in nanoseconds per op. Gosh, I got to get the right column here. Okay, there we go. So on the Mac for the P256, I was getting 27,000 nanoseconds per op. With our accelerated version on a Z16, it's 15,000. So it's certainly faster. Not quite twice as fast, but getting up there. And then you begin to really see the acceleration with P384, which is again, one of the 3 standard elliptic curve algorithms. This one took 359,000 nanoseconds per op, and we're at 31,000. So it's more than 10 times faster. And here we are again, I'm not sure what that is, 12 times faster. You can do the math in your head. So these instructions work really well and allow us to do some great acceleration on many of the standard cryptographic algorithms that are used every day. Whenever you connect to a website or whenever you um, want to transfer data securely, you're going to use one of the standard protocols. ECDSA is used to authenticate. When you authenticate with a server, almost certainly you're using ECDSA or either that or RSA. ECDSA is highly recommended because it's fast and efficient.
Hey, Bill, sorry, can I ask a quick question just while it's fresh in my mind? You talked about TLS, right? So presumably you can do read certificates.
Yep.
So certificates in USS are held in key stores like .pk12 and .p12 PKCS format. Do you have libraries available to read certificates held in key rings, RACF, ACF2, and top secret? And a lot of customers like to hold their certs there.
So we haven't done that yet.
Okay, no worries. Sorry, I didn't want to stump you there. Okay. All right. I mean, okay, fine.
There's lots of things on our to-do list right now. We haven't done that one.
Okay, thanks for your honesty,
No.
Bill. Sorry to knock you off balance. Go ahead.
No problem. Yeah, so Poly 1305, we had to do that manually. You can see that the algorithm, Poly 1305 algorithm, actually consists of a large number of multiplications. So here we have the first part of the message multiplied by something called R, which is a key or part of a key. And then we add the second part of the message and multiply it by the key, and add the third part of the message and multiply it by the key, and so on and so forth. And so, as you walk through, you might be doing, dozens of these multiplications. Now, these are not small numbers. Each of these is 130-bit prime, or 130-bit number modulo 130-bit prime. So these are big multiplications. There's no machine instruction to do these multiplications. And so we have to write an assembly language program to do it. And in fact, we do it schoolbook style, which I was always amused by when I first started doing this work, that basically we go back to essentially grammar school and start to multiply number by number, where the numbers, in our case, are in themselves large numbers, but at least they fit into a register. So I'm going to illustrate, this is a very small example. These are not big numbers. These are very small numbers, but it shows the technique. So I'm going to, do whatever the standard is, 5 times 6, first column 5 times 7, 5 times 5, and then the second column 9 times 6, 9 times 7, 9 times 5, and so on, just as we learned in elementary school. Except we're not going to do the carries on the fly. We're going to leave all those to the end. And because of the prime being, a number which is close to a power of 2, in this case, this example is close to a power of 10, but regardless, I'm just trying to illustrate the point. There's a trick you can use in order to simplify the operation of doing modulus. So remember, every time I do a multiplication, I have to do modulus of prime. So I simply move it over to a column, and then what is that I do? I believe, yes, I multiply by 3 in this case. So, the number that you multiply by depends on the primes involved and the prime factors. But in this simple example, I move it over to the first column, multiply by 3, and that automatically takes care of the modulus. I know it seems odd, but that is a mathematical trick, so that we'd use as many mathematical tricks as we can possibly do. And then we write a lot of assembly code. So these are assembly instructions. These are Go assembly instructions. They look very similar to HLASM, except in fact, the one peculiarity of Go is the operands are reversed. So with HLASM, this would be the target, and this would be the source. And in Go, this is the source, and this is the target. So you have to remember to reverse yourself every time you go through Go assembly. Oh, well, I just wanted to. Okay, so that's how we did Poly 1305. For some of the elliptic curve stuff, not ECDSA, but some of the elliptic curve stuff, we had to write assembly. This is my proudest moment when I figured out how to do modulus with Go, with in Go assembly with S290X instructions. So this is a very quick way, again, using mathematical tricks based on the prime and the prime factors of doing modulus for elliptic curve. Now, I'm not going to explain this because I don't even know if I remember anymore. This is from years ago, but I was very happy when I drew this picture, when I figured out how to do it. And that just as an example, so I wanted to show an example of how public key cryptography is kind of like magic. It allows you to share secrets in the open. It's quite remarkable, I think. Um, and the people, the two, Diffie and Hellman, who invented it, won the Turing Award, which is like the Nobel Prize of computer science, because it's just a remarkable invention. So let's imagine that we have Bob and Alice. They want to share. They want to share information. In order to share it securely, they need a secret key. So they're going to use public key cryptography in order to generate a secret key. But again, the channels on which they have to communicate right now are in the open. They don't have a secret key yet. So they have to do something where they can communicate on open channels and wind up with a secret key. So here's the mechanism. Bob picks a private key, just a random number. They have algorithms called cryptographically secure random number generators, which means they don't suffer from some of the sort of potential downfalls of a cheap random number generator. They generate random numbers that are as close to actual real random numbers as you can possibly get. But he just takes a random number, calls it his private key, and then does an operation. This is the elliptic curve operation called scalar base multiplication. So if you look in our library, and you can look on the source code that we have in Go if you're interested in that kind of stuff, you can see there's a definition of a function written in assembly called scalar base mul. And this takes this private key and turns it into a public key that can be shared on an open network. And he sends it to Alice, completely in the open. Anybody can read it, including, any malfeasance individuals out there. It's not going to do them any good to have read it. The important thing is that Alice reads it, and then Alice, at the same time, generates a public key and sends it to Bob. Anybody can read Alice's key. On each of their sides, Bob does another operation called scalar multiplication. Not scalar base, but scalar multiplication, where he multiplies his private key by Alice's public key. Alice multiplies her private key by Bob's public key, and magically they wind up with the same number. And it's secret. So that's the magic of public key cryptography. Although bad actors may have listened to these communications, they cannot share in the communication. They cannot generate the same shared secret key. So that is how public key cryptography works. And this is basically how we are able to communicate with each other today on the internet. So yeah, that's pretty much my talk. Open to more questions. And if you want to learn about the zOS container platform, here are some links. And I just want to ask for your feedback when you're done. And this is actually the right slide with the right feedback code. Are there any additional questions at this time?
Awesome. Thanks, Bill. Not at the moment. I know I'll just unmute Stuart. I'll see if Stuart wanted to be unmuted. If anybody wants to ask any questions, just go ahead in the chat, or because we're just winding to the end now, there's 8 minutes left, I'm happy to unmute anybody who wants to.
Thanks, Joe. Bill, you talked about the parallelism and the popularity of Go. Do you think that vendors are going to have to create extensions to their existing performance tools to be able to help with performance tuning around Go?
So I think existing performance tools will work. So when you build a Go application, you're building an application, right? So um, at the level of looking for bottlenecks, etc., um, I suppose if they're going to show the results in respect of the Go syntax. So for example, Go has a few built-in tools. So with Go, you can do a trace of your program and look for bottlenecks already. So that technology already existed built into the Go library. And I should have brought an example of that. That's a really good question. Maybe next time I'll throw in a slide on that. And we've used that profitably. Okay, so when we did this, sorry if I can find the right slide. Yeah, when we did this simple billion line challenge, right?
Yeah.
We actually used the built-in Go tools to track the performance, and it wasn't with this one, but it's an interesting point. Sorry, we were doing two things at the same time. There was a customer who was having a problem with a certain Go application. Um, Not written by us, but it was a module they downloaded, right? Um, and they were having a performance difficulty um, because they were sending and receiving files. Okay, it's an application for sending and receiving files. It's actually a good case study and how you can decompose this sort of thing. So I believe it was the sending of files happened very fast, faster than any other application they tried. So we're pretty proud of that. But the receiving of files was horribly slow, and they wondered what was the problem. Again, we didn't write the code, but we threw it into the Go trace analyzer, and it showed a very prominent bottleneck. So we were able to use the built-in Go tools for identifying the problem, and then we found a fix, and then we were able to actually, because it's open source, we put in a pull request on the module that was having the problem, and they accepted it. So that's now fixed in the wild. So now when anybody pulls that down to zOS, it will work perfectly. Yeah, so we have some built-in tools, and I guess what makes them useful is because they understand Go syntax. The other thing you could do is you could do a heat map. So a heat map is a way of saying what are the hotspots in the program. So it will actually profile the program, has built-in profile tools as well in Go, and then we'll sort of color code your program based on how hot those areas are. So we have some built-in tools. Vendors who have tools, well, I guess they'll have to maybe adapt them to the Go syntax, which is, it's actually very straightforward syntax. So I wouldn't call that, an extremely challenging addition, but nonetheless, yeah, maybe they would have to do a different version for Go.
Okay, and then the final question, because of time as well. But Joe and I are the stream leads on this track at GSE, and I was wondering whether you'd be able to hook us up with potentially a customer, or someone that's exploiting Go for something other than sharing internet proverbs, for our November face-to-face session to see if we could get a real world perspective of what Go has brought to that organization.
Yeah,
It's
I'd
really
love to do that.
exciting.
So can you Slack me your contact info, and we can get together and talk about that?
Can I leave that to you, Joe, as your
Yeah,
kind of
definitely,
internal,
Stuart.
so that we don't risk any leakage or anything? But if Joe doesn't mind working with you on that, Bill, that would be absolutely amazing.
Sounds
for
great.
this, because this is bleeding edge technology that should be exciting to many people who are attending.
Excellent idea. Sure, absolutely.
Yeah, Bill, I've got another few questions. I know we're running right to the wire. So is this available as it's available as a sort of optional download, right? It's not included in zOS,
That is correct.
presumably because the paint's still a bit fresh and you'd want to,
That's
you
right.
know, web the cycles faster. And I hate to put you from a management point of view, but if a customer uses this, what does it look like for support?
So you can purchase support. So you can get it from Shopsy and you can purchase support.
Okay.
We also, I'll be quite honest, we've done a lot of support and through the open community and also um, through the social media these days. So we're monitoring Discord and Reddit and looking for any questions that arise. So we're pretty open about support, on an as available basis for these other channels. But for official support, yeah, absolutely, you can purchase it and open tickets, and we'll deal with it.
Cool. Whatever project manager gets their paycheck funded by that support has just sent us a nice little, because that was an unprompted question to benefit IBM revenue. But the other one as well is a lot of the more modern kind of Unix system services based languages like Java and I think more recently Python. They're zip eligible. Presumably this isn't because it's compiled code, but
it is not.
Correct me on that one. Okay. And because it's low level, can it be used for writing exits? So I know exits, trues and glues.
Oh, you're the second person that's asked me that.
Oh, I won't be
in
the last.
2 days.
Okay.
So I don't have an answer to that, but it's very high on my priority list because you're the second person to ask me about exits in the last 2 days. So we'll have to put together a good answer for that, and we'll probably post it in one of our forums. But I don't have an answer today.
Cool. All right.
Yeah.
So we have about a few seconds left. If anybody else wants to ask a question, and Bill, what's the best way? You talked about Discord. What's the best way for folks to stay in touch with you? Is that the System Z Enthusiasts Discord community that gets
Yes,
run?
that's it.
It is.
I think
okay.
so. Yeah.
All right. In which
Oh,
case,
Discord. Or
would-
if you're an IBMer, you can Slack me, of course. But for external people, we do monitor Discord. Yeah, the Z enthusiasts. Yeah.
Okay, and I'll just post a link to that directly. I think you have
Right.
to have an invite link to join that Discord community, which is a bit strange.
Yeah. Sorry.
No, not at
Yeah.
all. But just reach out. I know folks on LinkedIn. Anybody's connected with like Stephen Perver or any of these kind of amazing folks out there, or Herbert Daly or Jaime Cooper. They're all seem to spend way too much of their work time in that channel. Brilliant. Thanks, Bill. Please give
And
your
I also
feedback.
I'm open to
Go ahead.
email as well. Somebody can just email me.
You have your email address. Do you mind if I post it in the channel, or
Go right ahead. It's fine.
okay, right ahead. I'll just see if I can
Bill
snarf it.
Bill at ca.ibm.com.
Bill O at
Yes.
ca.ibm.com. CA for Canada.
Yep.
Awesome. Thank you for that. That was really, really good. Thanks very much for that, Diffie-Hellman, that explanation of public-private key. It always generally, my brain kind of balks or short circuits when people explain public-private key encryption. And that was good. Good job.
Thank you.
You could almost do a whole hour just on that, actually, irrespective of languages. Yeah.
Yes, that's true. I'm trying to pack a lot in.
Cool.
Thank you very much, Bill. Excellent session.
Thank you.
Yeah.
Bye-bye.
+1. Stay safe, everyone. Cheers, Bill. Thanks, Stuart. Bye.
Bye-bye.